I'm introducing M. Hasan, a new PhD student in the Porous Media Research Group at the University of Nevada, Reno. He is from Bangladesh, and he completed his bachelor's degree from Bangladesh University of Engineering and Technology in 2016. After his graduation, he worked with different faculties of Bangladesh University of Engineering and Technology in different projects. He worked in industries as an engineer for a little while. He joined the Porous Media Research Group of University of Nevada, Reno in January 2018 as a master's student. For his research, he worked on developing a new solver for phase change and two-phase flow in porous media. He defended his master's thesis recently, and he will be continuing his studies as a PhD student at the University of Nevada, Reno, starting this fall. Please start whenever you're ready.
Thank you, Rick, for the introduction. So my name is M. Hasan. Today, I'll be presenting my work, which is on development of a numerical solver for phase change and two-phase flow in porous media. We all know that there is no atmosphere in space. As a result, the spaceships will experience extreme heat on one side and extreme cold on the other side. A lot of electronics are used to build spaceships. Miniaturization of these electronics can produce a lot of heat if we seek better performance from the electronics. So to protect these electronics from these extreme conditions, advanced thermal management system is required. For example, in 2021, NASA will launch the Surface Water Ocean Topography project, and this project will install advanced thermal management system to protect the electronics. Usually, NASA employs single-phase systems, but the single-phase system has very poor isothermality unless high pumping power is used. For a single-phase system, heat transfer involves with the sensible heat only. As a result, the temperature differences in the fluid is very large. On the other hand, for a two-phase system, liquid is evaporated, absorbing the heat from the electronic devices, and the produced vapor is transported to the condenser. The two-phase system is a passive phase change thermal management system, and these systems does not require any pump. It can achieve very high isothermality as it only works with the latent heat. Loop heat pipe employs this two-phase system where in the evaporator, liquid is evaporated and the produced vapor, liquid is evaporated in the evaporator and the produced vapor passes through this vapor line and reaches to the condenser. In the condenser, the liquid condensed to liquid again and passes through this liquid line and then finally reaches to the evaporator. The accumulator here used to regulate the loop temperature. The porous media inside the evaporator can produce pressure by the action of capillarity, and this pressure can drive the fluid to flow through the whole loop. If there is a pump in the liquid line, that will eliminate the need for the accumulator here, and this will assist the porous media for the fluid circulation. This system can accommodate higher heat flux. So the overall objective of our research is to develop technologies that can be used to design two-phase loop heat pipes in microgravity for space application. From the above discussion, we can easily say that porous media is the most important part of the loop heat pipe system, as both capillarity and the phase change take place inside the porous media. As a result, the main focus of our work is to develop a solver in the open form architecture that can model all relevant physics of flow and phase change in porous media. So to develop a solver, at the very beginning, we employ an existing porous multiphase solver in OpenFOAM, which is called the ImpESFOAM. This ImpESFOAM solver can perform simulation of multiphase flow in porous media. So we customize this ImpESFOAM solver by including the energy equation, phase change models, capillarity and relative permeability models, effective thermal conductivity models, and finally we added temperature-dependent fluid properties like density, viscosity, and thermal conductivity. So these are our governing equations. In the pressure equations, there is this vapor Darcy velocity. This one is the liquid Darcy velocity. This one is phase change term for the pressure. This is our capillary pressure here. There is also gravitational contribution in the pressure equation, and there is also relative permeabilities. In the saturation equation, there is transient saturation term velocity, and a phase change saturation term. This pressure and saturation equation were available in the impulse form solver, but there is no phase change term. Our first implementation to that solver was inclusion of the energy equation, where there is this transient temperature term, velocity, effective thermal conductivity term, and this phase change term. And this phase change heat, QPC, can be calculated from the phase change models. We have presented two different models here. One is the empirical rate parameter, and another is the interface equilibrium model. In the empirical rate parameter model deals with the every cell of a domain. When the temperature of a cell goes above the saturation temperature, the evaporation will take place. That means heat will be absorbed. When the temperature is less than the saturation temperature, condensation will take place. That means heat will be rejected. For the interface equilibrium, a scan will take place for all the cells in the domain to find the two-phase zone, and this QPC, which is the phase change heat, will be applied on that two-phase zone. To calculate the capillary pressure in the pressure equation, we have capillarity models. In this slide, we presented two different capillarity models. One is the Van Venetian model and another is the Leibniz model. The Van Venetian model was present in the impulse form solver, and capillary pressure is calculated based on the entry capillary pressure, saturation of the liquid, and there is a constant N. We have implemented this Leibniz model into our solver as a library, and the capillary pressure is calculated based on this interfacial tension, capillary J function, porosity, and the permeability. This capillary J function is calculated from this polynomial based on the saturation. From both of these models, we can easily say that with the decrease in the saturation, capillary pressure will be increased. To calculate the relative permeability in the pressure equation, relative permeability models are used. We have presented two different relative permeability models. One is the Van Venetian model and another is the Kalman-Kozeny model. The Van Venetian model was present in the impulse form solver, and the relative permeabilities for vapor and liquid is calculated based on the saturation. We have implemented this Kalman-Kozeny model into our solver as a library, and for this model, the relative permeabilities for liquid and vapor is calculated based on the saturation of the liquid also. To calculate the effective thermal conductivity, we used effective thermal conductivity models, and we have presented four different effective thermal conductivity model. One is a parallel, series, Alexander, and the She model. The most commonly used model is the parallel model. For our simulations, we also use this parallel model. But in some papers, we have found that the She model matches best with the experimental results. Our solver flow works. So when we initiate the phase change impulse form solver, then all the fields are created to solve the governing equations. For example, saturation, pressure, velocity, temperature, conductivity, these fields are created. Then it goes to the libraries. There are two different libraries. One is the source libraries and another is the developed libraries. The developed libraries includes all the models that we just discussed. And the source library includes the tools for creating mesh or defining different fields. After getting all the information from the libraries and the create fields, The phase change impulse form is then solve the governing equation to compute pressure, saturation, phase velocities, and also the temperature of the domain. We have presented two very simple example using our solver. The first one is 1D simulation, and for the 1D simulation, we use all constant properties. We also use leverage for the capillarity, Herman-Kozeny model for the relative permeability, empirical model for the phase change, and parallel model for the effective thermal conductivity. This 1D simulation is 10 centimeter long, has a permeability of 7 into 10 to the power minus 13 meters square, and a porosity of 38%. Initially, this 1D domain is fully saturated with liquid, and the temperature at the inlet is set as 300 Kelvin and the outlet temperature is 1580 Kelvin. A gravitational force is applied along this positive x direction. The pressure for both inlet and outlet is set as atmospheric pressure, or in other words, zero gauge pressure. So here we have this saturation contour and this saturation profile along the domain. And from this profile, we can easily see three distinct zone. One is this liquid zone, then there is this S-shaped two-phase zone, and there is this vapor zone. The two-phase zone is S-shaped because of the capillarity and the saturation relation. Here our liquid zone is 8.1 centimeter long, the two-phase zone is 1 centimeter long, and the vapor zone is 0.9 centimeter long. In this slide, this figure shows the liquid velocity along the x-axis. The liquid velocity at this liquid zone remains constant around 3 into 10 to the power minus 4 meter per second, and then in the two-phase zone it increases. It increases in the two-phase zone due to the capillary pressure, and then it decreases to 0 at the vapor zone because there is no liquid left. This figure shows the vapor velocity along the length of the domain, and at the liquid zone, as there is no vapor, the velocity of the vapor is 0. Then it goes negative to keep the mass conservation. Or in other words, we can say that in the two-phase zone, when the wetting fluid, which is the liquid, is advancing, the non-wetting fluid, which is the vapor, should be receding. And at the vapor zone, when all the liquid transformed to vapor, that means the liquid momentum will be transferred to vapor, then the vapor velocity will increases to positive. This figure A here shows the pressure profile along the length of the domain. The pressure decreases at the liquid zone. As a result, the flow moving from inlet to outlet, then at the two-phase zone, the pressure increases due to the capillary pressure, and also as the liquid converts into the vapor pressure includes this increase in pressure, and then the pressure decreases to the zero gauge pressure, which is the atmospheric pressure that we set for our case. Then this figure B shows the temperature profile along this simulation domain, and the temperature increases gradually in the liquid zone as the effective thermal conductivity is high. The effective thermal conductivity is higher in the two-phase zone. As a result, the temperature increase is little more than gradual, and it increases rapidly in the vapor zone as the effective thermal conductivity is very low. However, the temperature in the two-phase zone should be isothermal, but we found some temperature difference in our case, and we will be investigate this issue in our future work. Then this is another example, which is a 2D domain, and this 2D segment is from this 2D domain is from this evaporator section. And in this evaporator, liquid is advancing through the porous media, and at the interface of porous media and the metal casing, liquid is evaporated, and the produced vapor leaps through this vapor group. Here, the metal casing is the heat source. This 1 by 1 centimeter square porous media initially is fully saturated and has permeability of 10 to the power minus 11 meters square and porosity of 50%. There is no gravity imposed here. All the fluid properties are temperature dependent for this 2D simulation, and we use Van Gunsten model for capillarity and relative permeability. We also use empirical models for phase change, and we use the parallel model for the effective thermal conductivity. The inlet for this domain, for this simulation domain, the inlet temperature is set at 368 Kelvin and the heated plate is set at 378 Kelvin. The outlet is set at atmospheric pressure, which is the zero gauge pressure. From this segment at this evaporator, we can easily say that the walls should be the symmetric wall. Now this is our saturation contour of the liquid, and let's start a video. So the video is not working somehow. I'm not sure why, but
If you go out of present mode and then back in, you should be able to start it.
yeah. So yeah. So here is a video, and you can see that around this heated plate, the vapor starts forming. The evaporation starts happening, and the liquid saturation at this around this heated plate is 0.74. The liquid does not convert fully into vapor because the temperature at the heated plate is set only 5 Kelvin above the saturation temperature. The liquid accumulates at the outlet while the vapor leaves the domain. This represents the actual porous media behavior, as the capillary pressure here acts as a barrier for the liquid to leave the domain. Here we can see the temperature contour of the domain, and it's at the heated plate. The temperature gradient is higher. Higher temperature gradient, higher temperature can be seen, and you can observe lower temperature around this inlet, as the temperature at the inlet is set at 368 Kelvin. Here, in this slide, the liquid we present the liquid velocity along the inlet, and you can see this is not uniform. This is our inlet, and the larger velocity is observed around in the region which is above the heated plate, because around the heated plate the evaporation starts place. That means the liquid saturation will be decreased. With the decrease in the liquid saturation, capillary pressure will be increased. So the capillary pool will be higher around this position than these left places. And this figure shows the vapor velocity profile at the outlet. As we know, the vapor starts forming around this heated plate, then it will be converged to the through the outlet. So the velocity near the heated plate would be greater, and it will be decreasing by the increasing distance from the heated plate. So to conclude our work, we developed a numerical solver which is phase change in phase foam for two-phase flow and phase change in porous media. We have introduced phase change capillarity, relative permeability, and effective thermal conductivity models and temperature-dependent fluid properties to the solver. We have presented two simple examples to demonstrate the capabilities of this new solver. The first case is 1D simulation, which is performed with the constant properties. Our solver was able to qualitatively predict the correct behavior of the flow and phase change, but not the correct temperature profile in the two-phase region. The second simulated case was a 2D domain representing a segment of the porous wick of an loop heat pipe evaporator. Results showed that liquid does not fully convert into vapor when the heated plate is slightly above the saturation temperature, and higher vapor velocity and the temperature are observed near the heated plate. So our future work, our solver is not still complete yet, and it is still in the development process. So for our future work, we will continue improving the solver by fixing the temperature issue and implementing other phase change models. We will validate our solver with the experimental data, and this experimental data will be obtained from the quasi-2D experiment that is being constructed by our research group. We will finally couple the solver with a flow and phase change solver in open spaces, like for example, flow through a pipe, and this will create a robust solver that can be used for multiple applications. And this work was supported by NASA EPSCoR, and thank you.
Thank you for that informative presentation. If anybody has any questions, please post them in the chat. I know there's a bit of a lag, so we'll give people a minute for that. To start off, on slide 20, you compared your results to a semi-analytical model. What do you believe caused the discrepancies that you noted?
So actually, we changed that slide.
Oh, then
yeah. So yeah, with the semi-analytical model, because we are, as I was saying, we're still developing our solver, so it's too early to compare with the model now. After we fixing all the issues that we are having in the two-phase zone for temperature, then we'll be comparing our results with different models.
Okay, apologies. We got a question in the chat. Would you please re-explain the phase change model?
These two models. So we have these two models where it's the empirical model and the interface equilibrium model. So for our cases, we are working with this empirical model right now, and we are not started working with this model yet. So for this model, when the thing is like from the energy equation, we can find the temperature profile of the domain or temperature gradient of the domain. Now that we know the temperature of every cell of the domain, now when the temperature of any cell is greater than the saturation temperature, our this QPC will help to evaporate, and when the temperature is less than the saturation temperature, this QPC will be This QPC is used for the condensation. Like in our model, actually we use a if statement where we say that when our T is greater than T saturation, then use this equation, which is QPC. It's actually the Lee model, and we tell our code to use this QPC, and when our and then else if T is less than saturation temperature, use this equation for the condensation. So that's how that's how our code doing the phase change.
All right, follow-on question. What are S and R in your...
So can you repeat it, please?
What are the variables S and R?
The S is the saturation of the liquid, and this R. So we have this RL and RV. So these are the rate parameters. This one is for the evaporation, and this one is for the condensation. Actually, these values should be tuned according to your mesh sizes. So you have to tune these values to for different mesh sizes, and yeah, that's all.
All right, another question from the chat. You have thick liquid vapor interface in the 1D model. Is that reasonable?
This one?
Presumably.
Yes. Yes, because so with the semi-analytical model, which is developed on the local thermal non-equilibrium approach, and when they found their vapor length is around 2 centimeter, and for our case we have found only 1 centimeter. And yes, that this thick length is reasonable because like so we have there is like dissimilarities between that semi-analytical model and our model, because we have used different permeabilities. But when we fix this, we hope that when we fix these temperature issues, and also we use these permeability values according what they were using, then we might get what they get for their vapor length. Their vapor length is 2 centimeters. So yeah, that's why I think this value of the thick value of vapor is reasonable. And also we have our outlet temperature, which is fixed at 1580 Kelvin, which is way more than the saturation temperature. So that's why this is a reasonable length for vapor.
All right, thank you very much. I'm afraid we're out of time for questions.